that charging like this. I don't know if it's a charger. Well, there's no port for it.
That's because it's no, this is not it. Okay, this is.
This presentation, my batteries are on. So I don't have a charger, this is the same port. Well, this is USB-C to charge this amount. Well, the problem is you just email a USB-C.
I don't have a barrel charger up here.
I thought it was one of those.
That's the charger.
Yeah.
Here, no, here. Is there a USB-C over there?
No, that's the
But
problem.
there is this. Here. Nope, we got it. From the charger, is it?
That's not the charger, the charger.
Where is this charger?
It's balance. This is what-
Yeah, you should just do it through it, straight HDMI. There you go.
Okay. Cool?
Yep.
Yeah, cool, okay. Okay. Should be charging. Are you ready? Everybody ready? So, like AT had said previously, I do want to say thank you for all of you guys coming in, taking your time for this. It means a lot. We put a year of effort into this, and we really want to show it off to you guys. So we are Beeline 3D. I'm Bella, that's Tommy, and that's Hannah. And we are a group trying to solve the problem with 3D printer inefficiency. So Tommy can tell you a little bit more about what 3D printing is.
So for those of you that don't know, a little bit of background, what is 3D printing? A 3D printer is a machine that can create products out of plastic. It's an additive process that you can use in industrial or hobbyist environments. Some issues with it, however, are it's inefficient and it's slow. You can also run into a lot of errors. One thing that we want to highlight though is that it needs a lot of human interaction to use and start and stop prints.
All right, so our problem statement, we discovered that mass 3D printing using it in industrial settings is on the rise. However, this 3D printing still has a bunch of inefficiencies when it comes to severe downtime. So the time that it takes to restart your printer in between each individual print, it takes forever. And so we want to decrease that downtime because when you're doing industrial prints that take about 2 weeks on end, every second counts. So if you start a print on Friday and you can't restart the printer and you have all that downtime Saturday and Sunday, and then until you can touch it again on Monday, like that is a lot of time wasted for our company, and time is money. So you're wasting money as well. So we want to make mass printing a lot more efficient so it can be used more widely in industrial processes.
And one thing we do want to highlight is many of you might be thinking about like a traditional printer where like you can print 5 pieces of paper and then another 5 pieces of paper and you can keep printing until you got 100 pieces of paper in there and you can grab it whenever. But with something like 3D printing, it is one print at a time and you cannot send another print through if there's already a print there. Therefore, a human is needed to make that change, unless you have our as we were talking about, this is a problem that we have experienced, but also it is a problem beyond us. It is beyond this room. There are over 857 3D printing companies in the US, and 82% of them experience downtime due to the inefficiencies that come with 3D printing. And one of the largest inefficiencies is the need for humans to remove and restart prints. An hour of downtime can cost upwards of $250,000 for a company. Some of these companies have thousands of printers that are printing very large scale prints. So if they miss an hour, that could mean not having a print for an entire weekend, which is a huge deal and is a big cost sink for companies. In addition, we surveyed around 90 people. We went online and within our engineering class, and we found that 60% of those people surveyed stated that they were frustrated with the 3D printing downtime that comes along with having to restart that print and be there. In addition, we interviewed Brandon Hart, who is a CEO of a 3D printing company. And he stated that one of the biggest detriments to the entire system of 3D printing manufacturing is that, like, let's say his print finishes on Friday and he can't get to it till Monday, which was an extreme deficit for his company. So from there, once we had that problem altogether, we needed to come up with specifications and things that our product needs to do in order to be considered a successful product. So we've got a bunch here, including like working in OSHA certified like conditions. So facilities need to be maintained between 66 and 78 degrees and 20% humidity. Therefore, our product must work in those conditions. One of the biggest things we want to highlight is that our product must increase printer uptime by 5% or more. In addition, it must flow with the design of existing printers. We do not want to ask other like individuals and companies to buy another 3D printer just for this attachment. 3D printers are extremely expensive, even from a hobbyist scale. So this would be an add-on that can flow into existing printers.
Yeah, so we are looking at previous solutions to help decrease the downtime that we have. One of them is Bamboo Handy. So this is created by the Bamboo Lab 3D printer manufacturing company. And it decreases downtime and it increases efficiency by allowing you to control your printer from your phone. It's a little app on your phone, and what it allows you to do, I've played around with it, you can use the light, you can move it up and down, you can start a print completely remotely. However, the build plate must be clear for you to start that print, which means if I wanted to print from home, I could start one from school, but I have to go home, remove it, and then I can start another one. So you still have to be there to reset the printer. You can just start it remotely. And then our second solution is a BL Touch. How this helps is this helps to automate the bed leveling process. So when you 3D print, in order to make sure that everything works properly and each layer is stacked perfectly, you have to make sure your bed is level. That can be done manually by twisting the knobs at the bottom of the printer, or you can install BL Touch, which does it through automation. This helps because it helps make that time in between each print a little less for the human, because it can take forever to re-level a bed. However, you still have to be there. You still have to hit the button. You still have to watch it and moderate it in the same room as the printer.
So let's talk about our problem. Our problem was that printers are very inefficient, and part of this problem is human intervention. There's too much human intervention when you're doing prints. If you want to do multiple prints, it takes way too long to have to come in and replace the build plate. So what is our solution? Our solution is something that removes the product off of the build plate automatically with little to no human interaction. You can do this remotely from almost anywhere. And to start it, all you have to do is use our product, let it go down, and then print another print.
And this moves into, this is a big problem. This is a very big scope, and we really needed a way to get everything organized. We're three people, we're three high schoolers, so organization is on our name, but we decided to really put an emphasis on this in this project in order to create the best product that we could. So one of those ways that we did that was we used a Gantt chart system, which is basically a chart that has all the dates way up top and then everything that you could do. And as you can see, it goes down and down and down as we complete each of our tasks. It is also color-coded by each of us, or things that we might have done together. And this allowed us to really schedule our time. We had created a preliminary sort of Gantt chart to schedule it, and we made sure that our actual activity matched that. So we had a plan for the day, and we moved forward with that plan, and if we didn't achieve it, we would adjust.
So let's talk about some of our early brainstorming ideas. We had a bunch of diverse opinions on what we should do to remove a product. To start off, we had our roller design, which basically just moved the build plate out of the way and switched it with a new roll. We had a table which reduced vibrations, so instead of removing a print, it would increase in efficiency and reduce errors through vibrations. We want to go on. We have our slider mechanism, which was kind of our original concept for what we ended up with, which basically worked by tilting the build plate and letting the print slide off, very similar to how our current product is. And then we also had a revised design, which was a clip that adds on to this nozzle right here. Actually, and basically knocks the print off.
Yeah, so then in order to decide on a design, we went through our decision matrix process. We looked at things such as safety, compatibility, which is a really big one because again, we didn't want to force someone to buy a new printer. So that was something really zoned in on. Durability, consistency, and then we also took in our survey results. We took a survey of those in our class and in our school at the PLTW classrooms to see which one they thought was the best. We weighted each category based off of how important it is. So for example, compatibility is rated twice because it was so important. Safety is rated 3 times because we do not want to decrease the safety of 3D printers. They are house safe. You can 3D print them anywhere as long as you're using the correct filament. So we didn't want to take away from that. And then consistency is another one. So we decided on the clip mechanism based off of its score of, what is it, 55.5?
Yeah.
So then we have our final sketches. As you can see, we have an exploded view of everything that we need. And then we also have a final sketch here. And by doing this, we just kind of got a better scope for how we were going to assemble everything and how we're actually going to make this happen. So as you can see, we utilized 3D printing and laser cutting to manufacture each piece.
So moving on from there, so we took all of that sketching and we realized that everything could work, but the thing that really makes sure that this can exist in real life is CAD. So we moved on, got onto our computers, and created a prototype of our design. So you'll notice that it starts with a base plate that goes underneath the 3D printer. This allows, like, if anything needs to go underneath the 3D printer, it is all one flat level. And our removal assembly. So I'm going to zoom in on that for us. So we have a motor mount right down here. So this is a stepper motor. So it is a pretty common type of motor that you'll see on 3D printers. A lot of 3D printer hobbyists will have them around their house. And so we mount that right to our wooden plate that's on the bottom. From there, we have a shaft going up that is contained within that motor using a shaft collar. So I'm going to move up so you can see everything else. So we've got this entire scraper mechanism. This is what goes underneath the plate of the 3D printer. It is in a scraper shape with 2 magnets that come out. Those magnets latch on to the magnetic build plate. In addition, it is all ran on one threaded rod. That allows it to move up and up and up once it is stuck onto the build plate. One thing that I would like to highlight about this entire assembly is that this can all be manufactured in a hobbyist home. So like all of these 3D printed parts, like these can all be 3D printed by the user. Stepper motors are something that typically 3D printed users will have around. And this base plate could either be manufactured using general machining, drilling, and all of that, or we use the laser cutter. So although those are less common tools, our products could really only be a base plate, and they can 3D print and produce the rest of it. So this allowed it to be a very accessible product, which we found through our research that there was a lot of products that did this, but they did it with robotic arms or mechanisms that cost upwards of $500,000. And this is something that somebody can print using the filament that they have in their home. The last thing that I want to mention is we had a big emphasis on having this integrate with other printers. So one way that we did this was in our base plate, we had a bunch of slots. So that means no matter where the bed is in relation to like where they place this entire mechanism, they can move our product around to where it needs to be on their exact printer. So this allows it to be an extremely flexible solution.
So we'll move on to our prototype planning. Before we wanted to start building this, we came up with a plan on how we were going to manufacture each part and assemble them together. I won't go through each step, but some things I wanted to highlight were our wiring. Our electrical was pretty complicated, as well as our code was also pretty complicated to design and make sure it works. Other than that, we came out to a total of around 18 hours of build time for us. For the consumer, it would only take probably 5 to 10 minutes to actually assemble.
One thing we would like to highlight about all that wiring and all that programming, that would not be something that the user has to do. It is something that we did on our programming side. So we'll touch on that later about future improvements of integrating with other machines.
Yeah, so we have our cost and our bill of materials. So what we had to do to make this is we had to use a 3D printer stepper motor, and we have all the price added up, and it cost us $80. But it is important to recognize that we had to do a lot of external electrical components because we could not hook up straight to the printer due to companies fighting with each other, and if we used another company's product, it wouldn't work. So basically, if the consumer were to use this, their price would be a little lower because they wouldn't have to necessarily have all those electrical components. They could integrate it into the pre-existing ones that they have on their printer. But you see, we also use a lot of tools available to us in our classroom. So we 3D printed, ironic enough, we 3D printed our scraper and our motor mount. And then as Belle was talking about previously, we used the laser cutter for the wood. Those materials are also very renewable and reusable as well. So we weren't like wasting materials as well. They can be recycled, and they're very environmentally friendly as well, which is another plus.
All right, so moving into the prototyping process, although we did have that CAD, we had everything together, everything doesn't work all the time. We did have a lot of failed prints, our magnets breaking, there's a bunch of these prints not meeting our standards. And so this is all part of the iterative design process. We really made sure to take what we learned from our last design and move forward into something greater. And you can see that with all like 12 or so scrapers that we went through. Definitely the most coveted part of our design. But generally the prototyping process went out pretty smoothly.
Yeah, so this is our final prototype. We have a photo of the code from our Arduino, which is what we used to get the code to go up and down. We have a photo of the scraper from 2 different angles for you so you can get a better idea of how it works. And then that is our breadboard up there. So that is all our wiring that went into this. And we have soldered wires to make sure the connections work as well. Do you want to demo it?
We'll demo it later. I think.
Okay.
So before we get into our demo, I wanted to talk about our testing. So after we created our prototype, we set a bunch of tests that we wanted to make sure our product achieved. I won't go through all of them, but some of them that I want to highlight are it must increase printer uptime by 5%, which obviously it does. If you go to the next slide. It must flow with the design of existing printers. So obviously we don't want it to be too heavy. We don't want it to be too big. All for the consumer's sake, which it fit our specifications. And we also want it to be simple to assemble. We took a survey with 3 volunteers, and they all gave it a rating of 6.67 was their average, meaning that it fit our requirement for simplicity.
And the big number, we do have an 80% success rate, and we would like to show that off. So you guys can draw your attention to the front here.
So we have an example product of what someone might print, and then if we were to just run our program, the user would not have to use a laptop. It would be battery powered, but for the sake of this prototype, we're going to use a laptop.
And our product is that little like red cube on there. So you'll notice it is lifting up on that threaded rod right there. It's moving the build plate up to about a 60-degree angle, which we decided was probably the best with like iterative design process. It seems to be getting stuck on the skirt. Nuts. But it has been working 80% of the time. The skirt's given a bit of difficulty, which is a line of filament around there, but that is an optional solution. We do it because this 3D printer is not calibrated well, but a lot of 3D printers, you don't really need that skirt. So let's move that skirt. Do you want to run it again?
Yeah, another notable thing is that our code actually runs it 3 times back to back. So if it does fail that first time and you're not home, it will run 2 more times. And we're actually using one thing that's notable is we use a PI plate. And so the PI plate, what it does is it releases your filament once it cools down, but the big hint is that it has to be cooled down. So we have to create a delay on our product so that it is only starts when it's cooled down, or else it won't actually release the print.
Yeah. So you see, it did remove it. I've got it in my hand right here. So it has worked 80% of the time. It works like better with, this is a very, very small print. This is a print that we've made to really get the gears going, but most prints are this size or larger. And we did have like I don't know if we have one of them there. We printed like a little boat about this big, and that works almost 100% of the time. So yeah, one of those. So we have really tested this with a lot of different products. Just the smaller it goes, the gravity gets a little bit difficult. Okay. Moving forward, this brings me into our next steps. So we would really like to create a stronger scraper pickup mechanism. This will allow us to get a broader angle on our build plate as we lift it up, which is just more assurance that it'll work. In addition, we'd like to solder together our components. This will make it easier for the user and make the transportation easier. Right now we have a breadboard, which is just like a bunch of little slots that you can stick the wires into, which can be a little finicky. So we want to, in the future, solder together our components so we can deliver it off to our customers. In addition, we'd like to integrate our product into the 3D printer software. This is what I was talking about before, where this would be all connected into one big system where the user could use it remotely. A lot of 3D printers already have like an auto start, so we would integrate it into something like that. For the sake of a prototype and a proof of concept, it wasn't necessary, but it would be something that we would do moving forward. In addition, we'd like to test the product lifestyle, like how long does it go before it breaks. We have ran it for like 8 minutes straight, and it worked perfectly fine. But we would really like to see this in a household for upwards of 6 months to a year, and see how long and how little maintenance is needed. We predict that not a lot of maintenance is going to be needed. It has not broken in the scope of what we've been doing in the classroom. It's probably had enough time of about 30 to 40 minutes. But we would like to see that in a real household setting. Thank you. We'd like to open the room up for questions and comments.
I'll start. What was the most challenging part of your project?
I would definitely say, so we're all pretty much mechanical oriented. I'd say definitely the hardest part was either the electrical or the programming. We're not very good at programming, and this did require a lot, especially with an Arduino. I think we use C++, which is kind of complicated. So kind of getting over that learning curve of understanding how the programming works and how we can actually integrate it was probably the most difficult one.
You mentioned at the beginning of the presentation that there were some business statistics related to how much money businesses could lose from their 3D printers not functioning. And then you talked about it being for residential use. If this were going into the business side of things, would you anticipate the prototype being larger or smaller or staying the same? Because not all 3D printers are exactly the same, so I'm trying to understand what would be the use function.
So we wanted to create a system that worked, and so we worked with what we have. We all use the ones at home, so that's kind of how we used it. But if we were to put this into an industrial setting, we would obviously just upscale it. In proof of concept is what we were kind of going for. So if we were to find a larger motor and a larger gutted rod and a larger scraper, we're sure that it would still work on the industrial printers. We have to integrate it a little bit more, take a look at their build plates, but we really wanted proof of concept that it was possible to create an automated system that would work. So we kind of put it on the scale that we personally know how to work with.
A lot of businesses also can use enders. This is probably the most common type of printer. So we felt like this was probably our best point to attack.
In terms of determining our scope, we did, towards the beginning, there was conversations about, do we go business? Do we go residential? But we realized that this is a problem that is both. It happens to all of us. I mean, we actually, when we were making all of our little sketches, we didn't talk to each other, and we just created our sketches on our own. And all of us came up with a solution to fix this problem. Our problem wasn't even in our brain. It was just 3D printer efficiency. It wasn't human interaction. So all of us have experienced this problem, but I have worked in industry, and I worked at Caterpillar, and a big part of my job was 3D printing, and it was really frustrating because my prints always seemed to be 9 hours for the 8-hour work week. So I would start my print in the morning, and it would be an hour away from finishing. And I couldn't start another one for tomorrow, which has really reduced my time. So this is a problem that happens both in the home and in industry. So that is why like we didn't reduce our scope to one or the other. Any other questions?
So you used it and then you had to manually reset it. Is that normally how you do it, or what made you do that today?
So, like I said before, we're not very great at programming. So we haven't quite integrated it to the actual printer. If we were to be able to do that, which if we had another few weeks, maybe another month, we could integrate it into the printer's software, and the printer could automatically move back and reset it itself.
Okay.
So it's pretty much, I don't want to say simple fix, but it's definitely something that's achievable.
It's
So
a
does
step.
the user have to do the programming to do that then?
No, we would do it. We just wanted to get the proof of concept over the full experience.
In the same way, this comes pre-programmed, and this would come pre-programmed for the user. And the way that our design initially works, it can rotate into the build plate so long as the build plate is where it needs to be. Our only hurdle is what he was saying, with the build plate needing to be in the right position, and that's something that we cannot control from where we are standing right now. But if we integrate with the 3D printed parts, it would work. But in terms of our design itself, there's no hurdle that stops it from being able to restart. In addition, its standard position is to go up and then down. So it can go down with the build plate. And preferably stay in this right position.
So you had a slide where you talked about data in 837 or 857 different companies that are doing 3D printing. And you talked about a survey of 90. So can you put that slide back up? Because I was trying to make sense of what you had for your statistics there.
I'm gonna do it on here if you don't mind.
Yeah, so with our statistics, we found that there are companies to prove that 3D printing is as big as we say it is. We wanted to prove that this is actually being used, because I know most people, they just watch 3D printers on those YouTube videos of Mr. Beast making 5 billion printers of them. And so we wanted to prove that it's actually an industry thing, that this actually exists, it's actually used. But then with our survey itself, that was us asking other people what they thought was a problem and if they found this as a problem.
So the 82% of experiencing downtime, the 1 hour of downtime cost, and the 60% of people surveyed, is that out of the 857 or is that out of the 90?
This is out of our research personally. So this is like our peers, and we put it out on a bunch of public forums. This is just like worldwide international statistics that we found through a reliable source, like credibility. So it's been, it wasn't our research, it was someone else's research that we have in our works cited. So yeah, it was mainly, those are like the big time like worldwide numbers, and then the one at the bottom is us doing research within our peers and whatnot.
All right, it looks like we only have one more time for one more question. So,
Your success rate is 80%. How do you achieve 100%? What would be something extra?
Next step. So if you want to go to our next step slide, I'm not sorry. There's a bunch of different things we could do. One thing is upgrading the scraper. It's kind of hard. The main problem is when we lift the build plate up, it seems to slip out 20% of the time. So if we were to upgrade our scraper a little bit more, maybe make it longer, maybe make the walls a little bit better, or even add some sort of point of rotation back here, I feel like we could get that up to 100% or close to 100%.
Any other last minute questions, comments?
Good thinking.
You can ask me.